Okay, so today we're going to be talking about water quality and sewage treatment. And this is the sheet that you're going to be working from. You're going to be taking notes as you follow the presentation. So let's get started. All right. Now there's two kinds of water pollution, which we learned from a previous lesson. You have point source and you have non-point source. And we know that point source is a direct discharge into the water. You can point to the source. So this would be an example like wastewater from factories, and it can be controlled a little easier, not controlled perfectly, but it's easier to control than non-point source. A non-point source is indirect discharge into the water, and it comes from things like urban runoff and agricultural runoff. This means you cannot point to the source. This would be like trash on the road that filters into the ocean, and this is very difficult to control. Here would be your point source. We can follow this back to the factory that it's coming from. And this is your non-point source. We cannot identify exactly where this trash has come from. There's another type of pollution called thermal pollution. And thermal pollution is an increase in the temperature change. And it's usually caused by us humans and our influence. The things that we do, the stuff that we put in the water, polluting the air changes the temperature of the water. And it's going to change the temperature of the natural bodies of water, which will decrease the amount of oxygen that's in the water, and it'll kill aquatic life. Things like plants that's in the water and other marine organisms. From pollution, contamination plumes form. Now, contamination plume is an underground spread of pollution to our groundwater. So what happens is, when you pollute a certain area, it seeps into the ground. And you remember that seeping into the ground is infiltration. And then it percolates. And it gets down into our groundwater. And that groundwater flows. And when it flows, it picks up that contamination. And you have something that looks like this. This will be your contamination source. This is where it will percolate and then infiltrate, get right directly into the groundwater. Remember, our recharge zone is where the rain comes in, infiltrates, percolates, creates our aquifer. That water flows. It flows right into the area that's contaminated. Here you also have wells that are dug, and those wells will tap right into that contamination, which makes that well contaminated and unsafe for whomever's using it, whether it be a business, a school, a residence. And the water continues to flow, and it pulls that contamination all throughout. So just because one site may be contaminated, that could impact an entire community. Now let's look at some things that pollutants can do. There's 5 things that pollutants can do, and these 5 things are very important because these are the 5 things that we're going to focus on in determining the quality of the water. One is the change in temperature. Pollutants can change the temperature. It can increase it or decrease it, which is not good for aquatic life. It also can change the pH, which is also not good, and we're going to look at that. It can also decrease the DO levels. DO is dissolved oxygen, and we're going to talk about that. And it can increase the nitrate levels, as well as increase the turbidity in the water. This is all harmful to plants, animals, and humans. Now let's look at temperature, because these are all things that determine water quality. Temperature is important. If the temperature changes, that's going to affect aquatic life. So the healthy temperature of bodies of water should be between 25 degrees Celsius and 45 degrees Celsius. Anything below 25 degrees Celsius or higher than 45 degrees Celsius is unsafe. Another thing that we look at in determining the water quality is pH. Now pH is the potential of hydrogen, and it identifies the acid or the base levels in the water. And our range that we look at is from 0 to 14. So if we're testing the pH of the water and it comes in the range of 0 to 6, then that water is acidic. That means there's a presence of an acid. If it tests at 7, then it's neutral, meaning it has no acid or no base. And if it tests between 8 and 14, means it's basic. There's a presence of a base, and that's what we consider alkaline, like alkaline batteries. Normal pH of water when testing, we would say our normal pH for the water is between 6.5 and 8.5. So if we're testing water and it comes out 6.5, between 6.5 and 8.5, we would say that's okay, that's healthy. But pure water is 7, meaning it's neutral. There's no acid, there's no base, and it's very healthy. We would want our water to be at 7, but unfortunately because of environmental changes, 6.5 to 8.5 is what we normally get. We test our pH with these pH strips. It's called litmus paper. Some of you may have seen pool lifeguards test the water like this. But what happens is you dip this piece of litmus paper into a liquid. In this case, we're talking about water. And you have a chart that you measure it to. And if the paper will turn a certain color, and you put it up to the chart. So if you're looking at this chart here, if you dip the litmus paper in the water, and the litmus paper changes a reddish color, then we have a pH of 2. And you knowing, because you have the information in front of you, that a pH of 2 would mean it's acidic. But if the litmus paper turns about a purple color, then it would be a base or basic. Now every chart is a little different with colors. So for instance, this chart here has a little difference of colors. It ranges from a bright red to a purple. Now if we were using this chart and we dipped the litmus paper into the water and it turned like a lime green, we would know that it's acidic. If it turned like a pinkish red, then we know that it's basic. And down here are some common elements, or not elements, common things that range in the pH levels. For instance, 0 is battery acid. That means that's a strong, strong base. That doesn't mean battery acid is the only thing that's 0. It also doesn't mean the water has battery acid in it. It just means it's a strong acid. Ranging down to 14, that's a strong, strong base. Things like drain cleaner. Again, that does not mean that drain cleaner is in the water, and it does not mean that drain cleaner is the only strong base. It's just an example of a base. Notice our water could range between 6.5 and 8.5. So that should be, actually, this should be pulled over to here, which means that your urine and seawater are all in the same range of what we would consider common for natural water. Alright, pH is very important for living things. Take a guess why. See if you can figure out why would you say that pH is very important. Remember when we're testing the waters. Why would you say that's important for living things? Remember, living things have to live in the water, and they rely on that water. They rely on their environment like we rely on our environment to be a certain way. So if you're thinking that living things grow and survive in a particular pH environment, everything has a pH. If the pH is not correct, their growth and survival is threatened. So if they're relying on a specific pH and it's different than what they're accustomed to or what they need, then their survival is threatened and their growth. The next thing that we check when we're checking the water quality is the DO levels. Now DO stands for dissolved oxygen. This is the amount of oxygen that is dissolved in the water. And it's very essential, meaning it's very important for healthy streams and lakes. It's measured in something called ppms, which is parts per million. So it's measured in very small amounts. And this actually comes from the photosynthetic process. So it comes through photosynthesis, and this dissolved oxygen gets in the water. And we measure this. We measure the amount of oxygen that's in the water. If it's very low, then we know that the species or the organisms are in danger because they need it to be a certain amount. So far we've covered things that determine water quality, things that we look at when we're looking at water quality. We so far looked at temperature. We have to check the temperature. We have to check the pH, and we have to check the dissolved oxygen. That's not enough, though. We have to check all 5 things to determine if the water is healthy or not. The next thing that we're going to look at is nitrate levels. This is the amount of nitrogen and oxygen. These are nutrients. And these nitrates are needed by living plants, animals, to build protein. And it comes from things like fertilizer. And we talked about fertilizer that we put into our grounds, natural and manufactured. It also comes from sewage and industrial waste. There's nitrogen. Remember the nitrogen cycle. Nitrogen gets into everything. Oxygen is also in the atmosphere, so that also gets into things. So whenever something is put back into the ground, fertilizer, sewage, and industrial waste, it's going to also release nitrogen and oxygen, which is very important because it provides a protein for our living plants and our animals. So the sources of nitrogen in groundwater, because it's going to infiltrate and then percolate and get down here into our groundwater, these would be things like your fertilizers. Those are your manufactured fertilizers, your manure, wastewater application, stuff we put into our wastewater, your septic systems, that's your systems for filtering out when you flush the toilet, decaying organic matter. We talked about little bunny Foo-Foo passing away and him going into the ground, or your deer dying, or any of your organisms that die and they decay into the ground, and anything else that's naturally infiltrated into the ground. Now with this, sometimes farming, because farming does provide this as well as our natural life provides nitrates, you could come across something called eutrophication. Now eutrophication comes from a Greek word which means development. And eutrophication is the over-fertilization or the overdevelopment of water. The overdevelopment of fertilization in the water with nutrients. Too much of anything could be a bad thing. So if there's too many nutrients in the water, that's considered eutrophication. And this occurs when your water comes from runoff from farmlands, lawns, sewages, detergents, animal waste, and leaking septics. So it's overcrowded with these nutrients. And here's an example of eutrophication. Here you have manure and fertilizers in the farm. It dissolves into natural water. Your bacteria in the ground turns into nitrogen. We talked about that from nitrogen fixation. The nitrate then seeps into the groundwater. Too much of it, the fish are like, oh no, this is not good. And once the freshwater, the fertilizer, begins to accelerate, algae starts to grow. When the algae die, enough oxygen is consumed to kill off oxygen-breathing creatures because the algae is pulling that in. So eutrophication is not a good thing. So again, too much of anything is not good. The next thing we have to check is the turbidity levels. So let's go back again. When we're checking the quality of the water, we need to check the temperature. Remember, if the temperature is lower than 25 or higher than 45 degrees Celsius, it's not good. We need to check the pH. The pH levels have to range between 6.5 and 8.5. So you kind of have a checklist. Let me see, what's the temperature? What's the pH? Then the DO, the dissolved oxygen. What's the oxygen levels? Then the nitrate levels. What's the level of nitrates that's in the water? If it's too much, not good. If it's too less, not good. Has to be just right. Then we check turbidity. Now turbidity is the measurement of concentration of particles in the water. Basically, how clear is the water? How much stuff is in the water? Can we see through the water? Is it too much stuff where the water is unclear? And we measure turbidity in 2 ways. You can use something called a Secchi disc. And what happens is a string is tied to the Secchi disc. The Secchi disc is, and then the string has knots on it. And the Secchi disc is lowered and keeps being lowered into the water. And the Secchi disc is really big. It keeps being lowered into the water until you can't see it anymore. And it lowers, and as it lowers, it counts the knots at sea level. And once you can't see it, it marks off the knots. And you pull it up and you say, okay, if it was able to reach so many knots all the way down until then you couldn't see it, then you would say it has a low turbidity, because we can get the Secchi disc really far down into the water and still see it. If you go only 2 knots or a little bit of knots into the water and you can no longer see the Secchi disc, then you would say it has a high turbidity, because in very few amount of time or very few notches, the Secchi disc disappeared. Notice the Secchi disc is white and black for contrasting color so you can see it. Another way for checking turbidity is having a container and placing it against a red strip. And what you do is you fill the container of water, fill the container with the water, and you place it against the red strip. And notice here, you would say, if it looks like this, then it's low in turbidity, because you can see right through it. You can see that strip, no problem. If it's in this error, then it's still kind of low in turbidity, because you can still kind of see it. These would be okay waters, safe waters. Once we get over here and the red strip becomes less and less visible, this is high in turbidity, and that's not good. That means there's too many particles, too much stuff in the water. So again, when we're checking water quality, we have to go through the chart, through a checklist. We got to check temperature. We have to check pH. The DO needs to be checked, the nitrate levels, and turbidity. So there's 5 things on the checklist. Sometimes you need special equipment to check the DO and the nitrate. And without that special equipment, then you would resort to checking the temperature, the turbidity, and the pH. So how can we conserve water? Because we really want to conserve it, because if we use too much of it, that's not a good thing. So let's take a look at some ways that we conserve water. You want to use only what you need. And you want to jot down in your notes on the side, what does that mean, to use only what you need? Well, things like don't let the water run while you're brushing your teeth. Don't let it run too long before you get in the shower. Don't let your water run while you're doing the dishes, while you're washing your hands. Certain things like that, you want to use only what you need. If you are drinking a cup of water, you don't want to pour the rest out that you have not drank. Don't throw your bottles of water out that you haven't drank. Drink it all. Or recycle it. Pour it into a plant. Pour it into your dog bowl. Pour it into your cat bowl. Pour it into your fish bowl. But recycle the water, because it takes a long time once it gets down that drain to regenerate back into our water cycle. So again, take a moment to write down some ways how you can only use the water that you need, and how you can recycle water, because I will be asking you these. Now let's look at how to treat water. And another way that we have here, which we don't have to write down, is drip irrigation systems. We're not going to write that. But how to treat water, there's something called a sewage treatment plant, and we have septic systems. Your septic system is in your house, and it treats your water as before it filters it and takes it into the underground after you flush the toilet, or you let the water go down the drain, or the sink drain, or your shower drain, or your kitchen drain. Sewage treatment plants are large sewage plants that clean our water once it gets through the pipes before it filters back into schools, our homes, and businesses. So we're going to talk about sewage treatment plants. So if you flip your paper over, we're going to go ahead and talk about that now. Okay, so now with your papers on the back, we're going to look at wastewater treatment made simple. First of all, we need to think about what is wastewater and why treat it. So again, as we're going through this, you want to make sure you fill in the blanks on the back of your note sheet titled Sewage Wastewater Treatment. Now, much of the water used by homes, industries, and businesses must be treated before it's released back into the environment. We cannot just let it go down the drain and then put it right back with the business. If the term wastewater treatment is confusing for you, then you might want to think of it as sewage treatment. So when you hear wastewater, think of used water. So wastewater is used water. I'm not writing anything right now, just taking a look. Nature has an amazing ability to cope with small amounts of water waste and pollution, but it would be overwhelmed if we didn't treat the billions and gallons of wastewater and sewage produced every day before releasing it back into the environment. So basically, your environment has a great way of coping with certain pollutants and getting rid of it, but the amount that we pollute the earth with on a daily basis, if we did not treat our wastewater, then we would be doomed because our environment would become so overwhelmed. So treatment plants reduce pollutants in wastewater to a level that nature can actually handle. So now looking back at your notes. Wastewater again is used water, and it includes substances such as, and we're going to go through these substances that it includes. And you have your blanks that you're filling in. So wastewater includes human waste, species and urine. It also includes food scraps. So that does end up in your wastewater. Oils that are poured down the drain or tossed in the trash. Soaps and detergents. And also other chemicals. All of these things are included in our wastewater or our used water. All of these things that are included in our wastewater comes from three major things. One is our homes. From your sinks, your bathtubs, your showers, your toilets. You can write down a couple of examples. You don't have space to write them all. It also comes from our washing machines, your dishwasher. All right, so the next area that wastewater would come from would be businesses. Now, businesses and industries also contribute to their share of used water that must be cleaned. Businesses, schools, things, places like that, they have toilets, they have sinks. Some businesses even have showers. They also contribute to wastewater. And then you have something called storm runoff. And this is an example picture of storm runoff, where there's things from cars and buses, and when you wash your cars or you water your grass, all of that runs off into the drains. And you've seen how icky some of those drains could be. Just go back for 1 second. Because rain that runs down the street during the storm is not clean. Harmful substances that wash off the roads, parking lots, rooftops can harm our rivers and our lakes. This is not a pretty rainbow here. So why should we treat wastewater? Well, if you look here, you have these young men jumping into a big body of water that's filthy. So let's look at why we should actually treat it. One reason is for fisheries. So we want to care for our environment and our health for fisheries, because clean water is critical to plants and animals that live in the water. It's important to the fish industry, sporting fishing enthusiasts, and future generations. Most of us do eat seafood or rely on organisms from the ocean. Another reason would be for wildlife habitats. So our rivers and ocean waters, they teem with life that depend on shoreline and beaches. Remember the intertidal zone. They're critical habitats for hundreds of species of fish and other aquatic life. And you have migratory water birds, which use these areas for resting and also feeding, along with other organisms. Recreation and quality of life. Notice these people Swimming in the ocean at the beach. That's recreation. Surfing, boating, cruising. So water is a playground for us. The scenic and recreational values of water are the reasons why many people choose to live where they do. Some people live on the beach. Some people live in areas where there's shoreline. Visitors are drawn to these water activities for swimming, fishing, boating, and picnicking. Lots of times you go to the beach for vacation. And you don't want to go to a beach that's filthy, that's dirty, that's hazardous to your health. Another reason is for health concerns. If water is not properly clean, water can carry diseases. And since we live, play, and work so close to water, harmful bacteria has to be removed to make the water safe. Remember, we depend on water. We talked about that when we very first started talking about water, is water is essential for life. So what's our goal of sewage waste water treatment? The major goal is to remove as much of the suspended solids as possible before the remaining water is discharged back into the environment. So you want to get rid of as much stuff as we can before we put it back into the environment. And we do that with something called sewage treatment. And there's a primary and there's a secondary treatment. This is a sewage treatment plant looked at a bird's eye view. And there's primary and there's secondary treatment. So let's take a look at a short video about sewage treatment plants.
Have you ever wondered where all the rainwater goes? Or the snow once it melts? Or the water in your sink, tub, or toilet after you've used it? This wastewater flows through the underground sewer system to a treatment plant. The plant removes most of the pollutants, then releases the water into a lake or river. The underground sewer network feeds into a regional interceptor, which is a kind of sewer highway that runs to the treatment plant. The action begins at the plant's pumping station. It doesn't look much from above, but the building extends some 15 stories below ground, right through solid rock. The wastewater collects in huge underground wells. It's not a pretty sight. It's full of dirt, rubbish, and, well, you know the rest. It also contains high levels of phosphorus, a poisonous element in the nitrogen family, harmful to waterways because it promotes the growth of algae. The water flows from the wells to giant pumps that force it to the surface. The plant has backup generators to keep the pumps working in case of a blackout, and devices to prevent water from backing up should a pump have to be shut down for servicing. Once the wastewater reaches the surface, it flows through the pumping station down discharge channels leading to the treatment building. Along the way, it's sprayed with either aluminium sulfate or ferric chloride, two chemical coagulants. They gradually transform phosphorus in the water from liquid to solid, so it can be removed later on. Once the water reaches the treatment building, it flows through screens. This preliminary filtration removes any solids larger than 2.5 centimeters in diameter, such things as stones, paper, and plastic. Giant presses compact this rubbish, squeezing out the excess water. Trucks then haul the stuff to a landfill, where it's buried. The wastewater meanwhile flows into large tanks called grit chambers. Grit refers to the particles in the water, such as gravel, that are inorganic, meaning they don't decompose or burn. These particles, some as tiny as a grain of sand, gradually settle to the bottom. Then they're pumped out and trucked to the landfill. To remove organic particles, mainly phosphorus, they add a polymer, a type of chemical compound. This demonstration shows what happens. Remember, as the wastewater left the pumping station, it was sprayed with a coagulant. That transformed the phosphorus in the water into solid particles. The polymer solution completes the process. It binds those particles, forming what are called flocks, masses of phosphorus that look like snowflakes. They're heavier than water, so they sink to the bottom. And that's exactly what occurs in the plant's clarifier tanks. It takes about 2 hours for the flocks to settle at the bottom, forming a layer of sediment called sludge. A system of rakes and pumps collects it and transfers it to the sludge treatment building. Unless testing shows a need for additional treatment, the clarified, fully treated wastewater now flows to what's called the outfall, a series of channels that discharge into the river. In the sludge treatment building, they spray the wet sludge with another type of polymer. This further solidifies it, so that the filter presses can more easily squeeze out the water. Most of the sludge goes into giant incinerators to be burned. The ashes go into a landfill. The gas that the incinerators emit powers several machines that dry and transform the remaining sludge into pellets. These pellets are sold as organic fertilizer. When it arrived at the plant, the wastewater was full of contaminants that can harm life. Now, after treatment, it contains 80% fewer suspended solids and 75% less phosphorus. And it also smells.
Alright, so now let's get back to our sewage treatment, primary and secondary treatment. So like the video mentioned, it mentioned primary treatment. So let's look at primary treatment. Now, primary treatment removes only about 60% of the suspended solids. The first part is raw sewage. That's the screening. That's where it filters everything through like a coffee filter. And it filters the water, catching these large particles. You have plastic wrappers and paper and bottle cans and anything that cannot fit through this filter. So wastewater enters the treatment plant, passes through the screen, catches these solid objects and dead animals even. And that's that raw sewage. Remember, we talked about raw sewage yesterday in our notes. Then there's a settlement tank. And in the settlement tank, you have smaller particles like sludge that can sink. Remember, we talked about raw sewage being that sludge. And it will be filtered out. So like how coffee grounds are filtered, or these would be things like coffee grounds and soil and oil and scum. So the settlement tank is where everything settles and you get that sludge. Then you have a removing of the sludge. So wastewater then enters into a second section of sedimentation. So it goes through a second part of the settling tank within your settlement right here, and it helps remove additional sludge. And this is the organic portion of the sewage. So it lets it settle down to the bottom like it showed us, and then it gets that out. Remember, the goal is to remove as many suspended solids from the water before we put it back into the environment. Now you move into secondary treatment. Now, secondary treatment is going to remove about 90% of the suspended solids. And here is the aeration tank. So step 3 would be the aeration tank. But what happens in the aeration tank? You have pumping. The wastewater system relies on the force of gravity to move sewage from your home to the treatment plant. So wastewater treatment plants are located on low ground, often near the rivers in which the treated water can be released. So if plants is built above ground level, the wastewater has to be pumped to the aeration tanks. From here on, gravity takes over and moves wastewater through the treatment process. Then there's the aerating process. One of the first steps that a water treatment facility can do is to just shake up the sewage and expose it to air. This causes some of the dissolved gases, such as hydrogen sulfide, which smells like rotten eggs, and also taste and smell bad if it's released into the water. Wastewater enters into a series of long parallel concrete tanks, like they showed you in the video. Each tank is then divided into 2 sections. In the first section, the air is pumped through the water. As organic matter decays, it dies in the water, It uses up that oxygen that's pumped in there, so it's going to get that oxygen. Then aeration replenishes the oxygen. Bubbling oxygen through the water also keeps the organic material suspended, so it'll keep it lifted so it won't fall down to the bottom. And it forces it to grit, so it settles it right out. It can get it right out. And then grit is then pumped out of the tank and taken to landfills. And like they said, it's also sometimes sold as organic fertilizer. The fourth part is another settling tank, because that did not get rid of all of the things that it could get rid of, or that it was not able to get rid of everything. So this is the water is filtered again and removes any leftover small particles. Then the last part is the chlorinator. Finally, the wastewater flows into the chlorine contact tank, where the chemical chlorine is added to kill bacteria. Yes, our water has chlorine in it. And this could pose as a health risk, just as done in the swimming pools. They put chlorine in it to clean the water. Bacteria can pose a health risk to us, so we use chlorine to kill it. Just enough to clean the water, but not too much to harm us. The chlorine is mostly eliminated as bacteria are destroyed, but sometimes it must be neutralized by adding other chemicals. So we have to put chemicals in our water to kill and keep our water clean. And this protects fish and other marine organisms, which can be harmed by the smallest amounts of chlorine. So even though we put chlorine in there, we try to get some of it out, but some is still left in there. And then you have your water quality department, which says that certain things, as long as it's not a certain amount, then it's actually safe and it's okay. So we have certain things in our water that is deemed to be safe and okay, the chlorine, fluoride, the turbidity levels, and things of that nature. Alright, so then this includes your lesson. If you need to rewind it or go back to any portion,